Hi guys, let's solve today's Leetcode problem, which is problem number 3629. Minimum jumps to reach end via prime teleportation. Okay, it's a medium problem. Let's read this out. You're given an integer array nums of length n. You start with index 0 and your goal is to reach index n minus 1. Okay, from any index I, you may perform one of the following operations. Adjacent steps, jump to index I plus 1 or I minus 1. If index is within bounds. Okay, now prime teleportation, if nums of I is a prime number p, you may instantly jump to any number, any index j that is not equal to I, such that nums of j mod p is equal to 0. Return the minimum number of jumps required to reach index n minus 1. So this is what the problem is, where at every we have to start with index 0 and we have to reach index n minus 1, and at any point we can do these operation. One is adjacent steps we can take. So I am at index I can go either one step back, that is I minus 1, or I can go one step forward, that is I plus 1, where I minus 1 and I plus 1 should be within the bounds. Okay, or I can do the teleportation. What is the teleportation? If this number is a prime number, this index contains a prime number, so I can jump to any next number other than this in this direction or this direction, where nums of j mod p is equal to 0. Okay, so let's see this example. Here you see we have one. From one, where we can go, one is not a prime number, so either we have to take one step backwards or one step forward. Okay, so backward is out of bound, we won't consider that. We come to 2. From 2, where we all we can go, if we go back, so if we go back, 1 is already visited, so we should not go there. Okay, now from 2, where we can go, 2 is a prime number, one thing to notice. So we cannot just take plus 1 steps, we can also teleport to all the other indexes where this nums of j mod 2 would be 0. So if you see all this value 4 and 6, so 6 mod 2 is 0 and 4 mod 2 is also 0. So this is, we can come with one step. Otherwise, if there would have been more steps, still we would be able to come via teleportation. And same to the 6 also. So same we will do, we will start from this 1, we went to 2 because there is no other way, and from 2 we can directly go to 6. Okay, I mean we can go to 4 also, we can go to 6 also, and we went to 6, and this is our last index, that is n minus 1. So total number of steps required is 2 in this case. Okay, so this is what the approach is, I mean the problem is. Now let's think of how can we solve this problem. Now if you see here what we are doing, so we have these values and we are moving to next values wherever we can go, and at the end what we have to return, we have to return the minimum number of jumps required to reach this index, right? So what it says that minimum number of jumps, and from any index I we have certain possibilities, we can go this direction, other directions. And also the thing is, while going back, you see, I mean we cannot go back to the same index, that would be repetitive. Okay, so we definitely need to have something sort of visited, so that we don't visit the same index again and again. And then at the end we have to return the shortest path to reach n minus 1. We have to start from here and we have to go here. So since it indicates that we have to return the shortest path, that is the minimum number of jumps from I to n minus 1, where I is 0. So that itself indicates that okay, this is a BFS problem. Okay, where at every point we have to explore plus 1, minus 1, and prime exploitations. Okay, so these are the three possibilities, and we also, whenever we explore any new index, we will mark those as visited, and at the end we need to return the number of steps that we took to, or number of jumps that we took to reach this n minus 1. One more thing is, now let's say there would have something like 1, 2, 5, and let's say 11. Okay, so in this case if you see, there is no prime teleportation possible, but still in any case, in any provided example, we would still be able to reach this value n minus 1. Okay, this index, because we can obviously take one steps, right? So in this way we will be able to reach, so which means it is possible with the maximum number of steps, that is n minus 1 step. It was, but it is possible. Okay, now yeah, so this is what the problem is. Now let's say that the possible moves where we can go. One was the adjacent. So adjacents were adjacent jumps. Okay, so adjacent jumps where from I we can go to I plus 1, write it as I, we can go to I minus 1. Okay, and second is prime teleportation. Okay, so here if number is prime, so we are at I and this nums of I need to be prime. Okay, so then only we can do this prime teleportation. Okay, then we can jump to every index j. Then from here we can jump to every index j. Okay, not just one, all indexes j where nums of j mod this number prime number p, let's name it as p, is equal to 0. Okay, so there is where we can move. And since we know that each move, either we take this one or this one from nums of I to next nums of j, this is going to take the cost as 1 or the jump as 1. So at the end, using BFS, we can find the shortest path. Okay, and in BFS we know that every time the queue we pass all the things in the queue, right? And then we explore its neighbors. So it always tells us what was the shortest distance in which we arrived this index. Okay, so that is how we will know. Okay, whenever we reach n minus 1, that will be our shortest, because that is something BFS guarantees us. Okay, now for this prime observation, what we said, we are at nums of I, which is a prime. We will get to know how this is prime and all that. We will solve that also. But now let's say this is a prime, we know somehow. Now we have to go to nums of j and we have to see if this value mod p is equal to 0 or not. So what does this mean? Okay, so let's say we have this number p and we are checking for some number x. Okay, now what we want, x mod p to be 0, right? So in this example, let's say our number is 15. Okay, and let's say the prime number is, so I mean if you see 15, what is the prime factorization of 15? So 15 prime factorization is 5 into 3, right? Now if we do 15 mod 3, so it will give 0, right? If we do 15 mod 5, it will also give 0, right? So if you notice that this number which has these values as their prime factorization, and whenever I did mod with those values, it is giving me as remainder as 0. Okay, so which means that I can go to, if this number is prime, okay, so I can go to all the values where this prime p was the prime factorization. Okay, so let's say my prime number is 3 and in array the values are 3, 9, 12. Okay, so here in this prime factorization, if we write, so for this it will be 3, for here it will be also 3, for here you see 2 and 3. These are the prime factorization, okay, for these values. Now for 3 I need to know what where, because you see that for 15, with if we do mod with this prime factors, we were able to go, I mean achieve this value 0, which means from 3 we can go to 15, or from 5 we can go to 15, which means from 3 there is an edge to 15, or from 5 there is an edge to 15. So from 3 if we see, so these are all the prime factors, and we can go to these values. Okay, so prime factors, we can go to 9 or we can go to 15. Okay, so and these are the values where prime factors were 3. So there are all the places where we can go. So this is two things that we needed to know. One was the prime, if how will we get to know if this number is prime or not? And if we know the prime, then we also need to know what is which all values this 3 is the prime factor of. Okay, so we need to store few things. Here one is these prime factorization. Okay, so for every number that we will have, so in the constraint we can have this nums of I can be max 10 to the power 6. Okay, so for this number from 2 to 10 to the power 6, we will store prime factorization of all of these numbers. Okay, so we will pre-calculate this value. I'll tell you at the end all more details about this, but yeah, so we will store the prime factorization. Okay, and after storing the prime factors for all these numbers, now we need to know that from 3 where all we can go. So here you see 3 was itself a prime factor, then for 9 also it's a prime factor, for 12 also it's a prime factor. So in this case we know, right, that from 3 we can go to 3, 9 and then 12. But rather than storing the values, because there can be duplicate values also, right? um, in the array, let's say there is something 3, 9, some 4, something, 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 and then again at the end there is 9. So instead of just going to this 9, I can go to this 9 also, right, using teleportation. So instead of storing the values, we will rather store the indexes. Okay, so one was the prime factor which we stored for all these values, and another is the from 3 where all edges I can sorry, where all indexes I can go. So that will be kind of edges to those indexes from this 3. Okay, so we will store the edges, and edges would be nothing but where all I can go from any prime. Okay, prime teleportation. So here we need to pre-compute the prime factors, right? So as I told, we will do from 2 till the max value, which is 10 to the power 6, right? But I can't write for all of this. I'll just write for these value, the prime factors. So for 2, it would be 2. For 15, it would be 3 into 5. For 6, it would be 2 into 6. For 9, it would be 3. For 10, it would be 2 and 5. So these are the prime factors. Okay, this is my step 1. We have pre-processed this value. Now we will use it across. Okay, so these are the prime factors. But now also let's also discuss how did we achieve these values. Okay, now you might have studied in your school that to calculate the prime factors, basically the sieve of arithmetic, there we write these numbers like this. Okay, 1 2 3 4 and so on till 10, and then all these numbers, let's say we write this till 100. Okay, now we know that now we have to find the prime factor for 2. Okay, so we know that we start with this number 2. So this is, here you see 2 don't have any prime factor. So initially when we started with 2. Okay, so for 2 we see 2 don't have any prime factor, which means 2 is a prime factor. Okay, now since 2 is a prime factor, we can use this value 2 to cross out all the values. Okay, so for 2 we will cross 4. Similarly here would be 6, we will cross that, then there will be 8, then 10, and so on, we will cross some values. Okay, and then at the end 100. Okay, so with this, while crossing, what we actually did, that in this we will just fill these values. Okay, so here we see that 6 was also there and 10 was also there. So somewhere here 6 and somewhere here 10. While crossing this value 6, we know that 2 was the prime factor which crossed this value 6, right? So we will store that. And for 10 also, 2 was the one that's crossed that value. So we will store this. Now, so for 3, if you see, so 3 don't have any prime, prime factors. Here while calculating for 2, we will store 2 also. Okay, now for 3 we see 3 don't have any prime factor, so same thing will do. So for 3, next value would be 6, so 6 we will write here as 3. Then we will go, there would be 9, so somewhere 9 would be there. For 9 also we will write 3, and so on, we will cross all the values. Okay, so crossing is nothing but storing the values. Okay, actual values for this prime. So in general, in Sieve of arithmetic, I think we store true or false, right? If that was a prime number or not. Here, for every number, we are storing its prime factors. Okay, the actual factors. So yeah, that is the one difference. Now, for 3 we found, we explored, or then here for 3 also we will store this as 3 is the prime factor of itself. Similarly, we'll do for 4, and now let's say we did for 5 also. I'm not doing. Now when I came to 6, right? So if for 6, I see that it already has some factors. Okay, it's not an empty set. It already has some factor, which means 6 is not a prime number. And since 6 is not a prime number, which means in this sheet, if you see, this 6 was already crossed, which means this was not a prime number. So we cannot use this value 6 to cross further, multiplications of 6, like 12, 18 or so. We won't use. So here in books, we studied that we use these values to cross which were left over. So 2 was, when we did for 2, 3 was left over. So we did for 3. Now here if you see 5 was also left over. 5 was not cross something beforehand. So we used 5 to cross over all these things. Now for 6 we see 6 also we have not 6 we have crossed, so we won't use this value. And likewise we will fill all of these values, okay, to calculate the prime values. And how we will do? So we from 2 we got to this value 2, 4 and then 6, right? So for 2 we can push this value. Okay, 2 was the prime factor. We came 4, 4. Okay, 2 is the prime factor. Now 6. Okay, 2 is the prime factor. 10. Okay, 2 is the prime factor. So for 2 we are doing for all the values, and wherever we find that this is I mean we won't find it, we are going to its multiplications only, right? So for all of these values we will push those values into the prime factors. Okay, so this is the prime factorization part. So I mean just for an ease, because this problem is about something else, I'll write the code also for this. Okay, so how are we going to calculate sieve? So for I is equal to 2, we will do tool the max value, and here we can initialize something. Max is equal to 1e 6 plus 1. Okay, and here we need to check if this factors, or I would write it as prime factors. Okay, prime factors of I is empty or not. Okay, because if it is empty, as in the case of 3 and 5 we see that, then only we will use that as our prime number, because that is only prime number which would be the prime factorization for other numbers. So for if that is the case, then what we will do, we will go to all the multiplications of these this prime number, and we will add that as their prime factorization. Okay, so we will run another loop that will go from I till j less than max value, and here prime factors of j. Okay, dot pushback I. Okay, so this prime factor here we did for 6, we pushed back 2. Okay, so 2 is the prime factor. Yeah, so that is how we are going to find the prime factorization. And here you see what is this looks like. This something looks like adjacency list only, right? Where we have our numbers and it prime factors. So this is the prime factors that is here, right? So that would be nothing but a vector of array. Okay, and prime factors of this max value. Okay, so yeah, this is about the prime factorization that we did. Our first step is done, where we calculated the prime factors. Now we have to calculate the edges, that is the prime teleportation that we are going to do. Now yeah, we will create the edges. Okay, so edges would be something like from this edge P. Okay, this will be our edges, and we need to know that where all we can go. Okay, so from where we go, from prime only we can go, right? So prime and where all indexes we can go. Okay, so this is what we need to store, right? Now in our example, if you see, we have these prime factors. Okay, I'll just quickly write it. Now we need to know like from where all we can go. Now in our array we will start with this value 2. Okay, we need to calculate this edges, right, from prime numbers to their indexes, where all indexes I can go. Now for 2, what are all the factors of 2? So for 2 I know only 2 is the factor of 2, right? So in 2 which is a prime number, I will push what value? I will push this index I. So 0, 1, 2, 3, 4. Okay. So I will push 0. From 2, I can go to 0. Now I came to 15. Now from 15, what are all the prime factors? So for 15, it is 3 and 5. Okay. So in 3, I will push this index 1. Okay. Because for 15, we know these are the prime factors. So for 3, what we will do? First for 3, we will push 1. Then for 5, we will push 1. Okay. Now I came to 6. For 6, what are all the prime factors? 2 and 3. So for 2, I will push 2 is this value. And for 3, we also push 2. Okay. Now we came to in this index 9. For 9, what are all the prime factors? It is 3. So for 3, I know this index 3. Okay. Because index 3 stores the value 9. Okay. So which means that from 3, where we can go? We can go to 9. Now, what is the prime factor for 10? That is 2 and 5. Okay. So 2 and 5. So for 10, what 2 we can go to 4, and 5 if you see. So here also we can go to 4. Okay. So this is the prime values and their indexes where all we can go. We have stored this. Okay. Now we can from 2 we can go to these values. From 3 we can go to these values. From 5 we can go to these values. So using these prime factorization, we derived our edges. Okay, where all we can go. Now using these edges, we will see that how we can go from index 0 till n minus 1 using the adjacents and the prime teleportation. Okay. So now let's understand the BFS part. Our normal BFS is that we have these values pushed into queue. Okay, let's say I started with this value 2. So from 2, I mean initially I can push this index. Okay, in queue I will push the indexes. So I push this value 2. Now from 2, where all I can go? So from 2 I can go to I mean from index 0 I can go to minus 1, which is out of bound, we won't explore. From 0 I can go to this is adjacents. Okay, I can go to 1. Okay, so 1 is 15. So I will write, okay, after 0 we will go to index 1. Now this was the adjacents. Now there is one more exploration that we need to do, that is prime teleportation. So from 2, where all I can go? So here this tells me from 2, and from 2 we can go because 2 is a prime number. That's why we can go to 2 only. I mean, if it would have been 15, we won't explore the prime teleportation part because 15 is not a prime. But since 2 is a prime, and how we get to know 2 is a prime? Here we have the prime factorization. And here we see for 2 only this is storing a value 2. So 2 is only divisible by 2. There is only one divisible. So which means this is a prime number. So here in this prime factorization uh, list that we have, we will get to know if this value is a prime number or not. Since 2 is a prime number, so we will explore the prime teleportation possibilities also. Okay, so from 2, where all we can go? So this now edges that we have calculated, this will tell us where all we can go to 2 from 2. So from 2 we can go to 0, 2 and 4. So 0, we already have visited 0 because we are at 0 index. Now we will go to 2 and 4. Okay, and both of them will take one uh, cost or one jump if we go to 2 or if we go to 4, because this is using teleportation. So now we will push this value 2 and 4. Okay, our queue has these value pushed. We started with 0, we will pop this value, and then we explored all the neighbors. So these were the neighbors prime teleportation. So this was 1 and this was 2. Okay, so yeah, this was the few things, and after this we will keep on exploring, and we will keep on marking the visited also. Okay, whenever we explored adjacents, we will mark those as visited. Okay, so that we don't revisit these values. Whenever we explore prime teleportation adjacents, we'll mark those as visited, and at the end when we have explored all the prime teleportation, right? Basically from 2 where all we can go. So from 2 we explored all of this all together, right? So we can go till all of this all together at once, because all of this will take only one jump, right? So that is how this BFS gives us the shortest distance also, right? So we explored all of this at once. Okay, now from 2 we know that we explored all of this, so this will give after this, because we were marking visited, which we will already do, but we will also delete this from our this adjacency list. Okay, why? Because if this still remains there, then we will again come and we will again explore 2, because we can come to C2 again in this array, right? Then again we will visit this. Okay, the 2 has this adjacent, 2 has this adjacent, but we have already explored all the adjacents of 2, so we not need not to revisit 2 every time. So for that reason, we will delete this list completely. After exploring all the prime teleportation for 2, we will remove that list itself entirely, because we have explored that. Okay, so that we don't revisit it again. Now, yeah, so after this, we will keep on calculating. So we we started with this 0, we explored all of this. Okay, wherever I can go with one jump. Okay, adjacents and then prime teleportation. Then we will explore this adjacents. Okay, we are exploring all of this at once. Okay, so whichever gets to n minus 1 index first, there, and we keep on adding our answer. Okay, from here to here it was one jump plus one, from here to here it was one jump plus one, and so on. And whenever we get this n minus 1, then we will return our answer. Okay, this was our answer, uh, whatever result as a jump that we have stored. Okay, so yeah, that's all about this problem. Now let's write the code for it. Okay, we will be given nums array, so I will store this size in n nums dot size, and we will have this unordered map to store the edges basically. Okay, so we were storing the edges above, right? So that was what, a prime comma list of indexes. So same, we will store int comma vector of int and this edges. Okay, now we will iterate over the array, and after iteration we need to know all the prime factors. Okay, so whatever the prime factors that we have for this number in this index I, so auto factors. Okay, I would write it as factor of this prime factors that we had, right? We stored this prime factorization of this nums of I. So what we will store in this edges, so this was our factor, right? So prime factorization will have something of prime numbers, say 2 into 3 or whatever, as the prime factor of any number or whatever. So for this factor we need to store where all I can go, right? So I will push back the index, where all index I can go. So what is the index? This is I. Okay, so we have now calculated our edges. Above I have written code for writing the prime factors also. Okay, now we have written our edges, that for this edge, these are the prime factors. Basically this contain the list of prime factors, and we are going factors by factors, and we know that from this factor I can go to the to this index. Okay, so that is what we were storing above. For this factor, these are where all the indexes where we can go, so we have now stored that value. Now we will have our jump that we need. Initially we will initialize with this with 0, then we need our visited array that will be of size n and initialized with 0, and we will have q int q, and in q we will push the initial index 0 to start with, and we will also mark this uh, in index 0 as 1 because we are starting with 0 and it is already visited. Now we will iterate over this until the queue is empty. Okay, queue is not empty, then we need to go over and see. Now we are exploring all level wise, I would say that we were at this index 0, then we explored all the neighbors, then these are the list of neighbors. Then for all of this, now we need to explore the next neighbors. Okay, then we got the next neighbors, then for all of them we need to explore the next neighbors, right? So that is why we need to know the size of the queue. So I'll store as is equal to queue dot size. Now we will iterate on this size, and I is equal to 0, I less than size, and I plus plus. Okay, now here what I need to do, I have this size, I am now iterating on this size. Now I need to find the index because this queue store the index, right? Index of the numbers. So I will get that value that is stored in the queue index ind is equal to q dot front. Okay, from this I will get the index. Now I can do q dot pop. Okay, now first thing first, we need to check if we have already reached this index which we are there, if this index is equal to n minus 1, if we have reached or not. If yes, then we can return whatever jumps, number of jumps that we have calculated, we will directly return that. Okay, if not, then we have the two exploration to do. One is the adjacents, in that we have the left and the right adjacent. So let's explore the left one first. So we also need to handle the boundary cases, that the index that we are going to calculate, right? So that need to be greater than 0. I mean, while going back, that should not be the case that we are exploring something minus 1 or minus 2 index, because that is invalid, right? So index should be greater than 0 and it should not be visited. Okay, visited of I n d minus 1. So if that is the case, then we will mark this visited of ind minus 1 as 1, and in queue we will push this ind minus 1 as the next index to explore. Okay, so this was the left adjacent. Okay, now we will explore the right adjacent. So if ind is less than n minus 1, okay, so we cannot exceed the last index, so it should be less than n minus 1, and uh, not visited of ind plus 1. Okay, so we are exploring the right adjacent, right? So it should not have been already explored, but now since we are exploring, we will mark that as visited as 1, and q dot push ind plus 1. Okay, so this was our right adjacent. Okay, now we need to explore the prime factors. So we have already stored the prime factors list, so that same we will use. So this is basically to check if this is a prime number or not. Okay, so in prime factors of this nums of ind, okay, we need to check the size of the list, the prime factors. If that is equal to 1, okay, then in that case we will explore, because this is a prime number and we can do prime teleportation from here. So we will store this in a variable prime is equal to nums of ind. Okay, here we need to check if we got to know this is the prime number. Now we need to see if this prime number is there in the list or not, because I said, right, we will be clearing out the list once we have explored all the adjacents from there. Basically from a prime number, if I have explored all the prime teleportation where all I can go, I will erase that list, right? So I need to check if this edges that we have, it has this value, or I can say the count for this prime is there or not. Okay, If then only we will explore its neighbor. So what we will do for auto j edges of this prime, we will explore where all I can go. Okay, this j is basically all the indexes from this prime number where I can go, and if that is not visited, okay, of j, then only I can go, right? Then I will mark that as visited and I will push that into our queue. Okay, visited equal to 1 and q dot push j. So this is the next number from where I can go, the next index where we can go from this prime number. So it is not visited and we went to that, and we have pushed that value into the queue. Now after all this, we have explored all the places where I can go from this prime number, right? All the edges. After that, since that is already explored and pushed into queue, we will remove that, okay, from our edges. So edges of prime dot clear, okay, we will remove that from our edges. Yeah, so that is, we will close all the braces and all that. And after this, here, after this loop, because this is where we are exploring all that, right? That this was from here we started, and these were all the places where I went. Now since I've explored all the neighbors, so this was one jump, right? Now here, from here we will explore no next neighbors. So this was one jump, so we will increase the value of our jump plus plus, and after this we will return the jump. Okay, so yeah, that is the this is the code for this approach. And I have already explained this prime factor calculation part over here. If you have not seen, you can go back and see. So yeah, this is where how we will go and calculate the prime factor, and rest is this. Now let's discuss the time complexity for this approach. Okay, so time complexity for pre-processing the prime factors that we were calculating, so that is nothing but O of n log of log n. Okay, so this is the prime factorization calculation time that it takes. And for BFS, we can say that we have this kind of loop where it is for all the nodes, indexes that we are going to visit, and we are going to visit those indexes only once. But here we see that we are also visiting the prime factor relations, right? uh, if it has a prime factors, then we are also exploring it. Okay, so altogether I can say that log of the max value that we have, okay, because that is where the prime factors that we are going to calculate. So yeah, this is the time complexity. And space complexity, if we see, so we are going to store this prime factors and the adjacency list. So this is the space that we are going to store the prime factorization. So it is n of log of n. Okay, and this n is nothing but, I mean, not n, it's actually mx, the max value that we are going to take to pre-calculate. So this is the space and time complexity. Now let's understand, if we directly write this prime factor method outside and just call it from our function, how will that hamper? Okay, so this itself takes n of log n time, right? So now for every test case, let's say there are so many test cases. For every test case, let's say there are n test cases, and then every time we are pre-processing these values, right? So it will take n into n times altogether, roughly. Okay. So rather, what we need to do, instead of putting this inside the class that we are calculating, right, we will uh, we need to store this in some global or static storage. Okay, we need to allocate this value and use this forever. Okay, so that it's not created for each function call that we make, or for each every cases, rather for each run how many test cases it run doesn't matter. For each run, this value will be initialized, and at the end, that value will be initialized and used for all the cases. Okay, so this prime factor will be uh, basically calculated for a run, and because that will be allocated in static memory, and that will be used for all the cases. So that is how we are going to do this. So I can now just write the static allocation for this. Okay, here first we have this as a constant variable that will, and this entire piece will be outside our class, and this need to be in the static block. Okay, so we have this prime factors list, adjacency list, kind of, list of array, vector of array. So this is a constant variable, and this block need to be static. Okay, so in C++ how we do is, so we will write it as bool initialized equal to this, and at the end we return true, and yeah, so this is a static block we write in C++. And if we didn't write something like this, right, or we would have written this into some method, and then we could have called from our function that we have written above, so this will not work. Okay, that will give us a TLE. So this is how we can uh, be safe from TLE. So we are going to initialize this once, and for all the test cases this will be initialized once. For every run it will be initialized once and used for all the cases. So this is the pre-processing that we are going to do. Okay, so yeah, that's all for this problem. I hope you like this video. Thank you for watching. Stay tuned for next videos.